All right, and so this next chapter, we're going to sort of, we've discussed these a little bit already, or at least we've seen them in lab. Now we're going to discuss them more formally here, these transition metal complexes. All right, and so just to remind us where we've seen these before, we had that equilibrium lab where we mixed iron 3 and this polyatomic ion, SCN. Does anybody remember the name of that? Thiocyanate. Yeah, thiocyanate. Should make a little bit more sense when you get to organic chemistry why it's called that. But anyway, these two things combined together, and they didn't form a normal ionic compound where the charges were all balanced. Instead, they formed this complex. And your job was to determine what this X, Y, and Z was. All right, it turns out that there are 2 of those thiocyanates, meaning that this has a -1 charge. And this was not a normal old ionic compound. This is what we call a transition metal complex here. All right, if you remember, one of the things that we took advantage of was the red color. We measured how much red there was to figure out how much of this complex had formed. That's a common property of these transition metal complexes here. They tend to be brightly colored. So we're going to explore those properties. We got a little bit of groundwork to lay here first. All right. So first of all, the formation of these complexes is kind of like rooted in a lot of what we see over and over and over again in chemistry. All right. This sort of fundamental principle where electron-rich species react with electron-poor species. Okay, and this is this fundamental concept that we're going to see over and over again in chemistry. In organic chemistry, or rather in inorganic chemistry, they have a tendency to call these electron-rich species Lewis bases. All right, we were kind of introduced to this terminology before. I know everybody's favorite part of the course is vocab. And the electron-poor species would be the Lewis acids. In organic chemistry, the same exact phenomena occurs. Electron-rich species react with electron-poor species. They tend to have different names for it. In organic chemistry, we call those electron-rich species nucleophiles. Does anybody know what that suffix "phile" means? Yeah, like something, a lover of something, right? So a nucleophile is something that really wants a nucleus because itself is electron-rich. And an electrophile is the exact opposite. It really wants electrons because itself is electron-poor. All right, but this is what we're going to sort of see. This is how our understanding of why these complexes form, and this is just something we'll see over and over again in chemistry. Electron-rich species, they react with things that are electron-poor. All right, so we're going to make a complex here. Let's say that we take this iron 3 ion. Okay, if we put it into water, it turns out that it doesn't just form a normal old aqueous solution, but these water molecules, for being good in drawing our Lewis structure, the oxygen has these lone pair of electrons. All right, so let's think here. This transition metal ion right here, is this electron rich or electron poor? It's electron poor because it's got that positive charge associated with it. But water's sitting over here with its lone pair. It's electron-rich oxygen. And so what happens is that lone pair will form a bond with that transition metal ion. All right, and it turns out you don't just get one water molecule that forms such a bond, you get a few of them. Whoa. All right, so another water molecule, again, it's got its lone pair that will reach out and form this new bond with this iron ion. All right, we're going to make 4. We're going to decorate this thing with 4 water molecules here. This one, let's just note, I'm kind of writing the formula a little weird. Instead of H2O, I'm writing OH2. And that's because I want to show that it is the oxygen with its lone pair that is forming a bond with the iron, not the hydrogens. All right, so you'll see this where we kind of play with these formulas a little bit to show how these things are actually oriented. Okay. So this thing right here is our transition metal complex ion. And we're going to be good because it has this net charge. Each of those waters have a charge of what? Just 0. They're neutral. So that central metal ion in this case is the only one contributing to charge. But this whole thing has this charge of +3. And this is what we call our transition metal complex. Complex ion. More often just referred to as a complex ion, or even more shorthand, just a complex. All right. These bonds that it forms here, what type of bonds do we have that were this shared pair of electrons? So those would be covalent bonds. These ones are kind of a special type of covalent bond, and we'll discuss why they're special. They're kind of just like a different theory that underlies them. So these are what we call coordinate covalent bonds. All right, they are shared pairs of electrons as in our normal covalent bonds, but they don't really follow the same underlying theory. And we'll talk a little bit more about that when we get on here. Okay, the iron in the middle, that's your central metal ion. All right, and the things on the outside, in this case, these water molecules, we're going to see a bunch of different ones of these. We call these the ligands in our complex. Water is a common ligand. There are other common ligands that we're going to see as well. All right, and some of these things you can actually isolate into a salt. So if we paired this thing up with 3 chlorides, these would just be playing the role of these counter ions. All right, then that whole thing together would be what we would call a coordinate compound. All right, our main focus really is going to be on this bit right here, right? These transition metal complexes. This is what we're going to sort of discuss ad nauseum this week. Cool. Before we can kind of introduce this fancy theory called crystal field theory about these complexes here, we need to kind of review some stuff that we should know from Chem 1A. And I know everybody's been practicing this all summer long or whatever, winter long. But let's go ahead. We're going to review electron configurations. All right, so first of all, our electron configurations, they tell us where the electrons live in an atom. All right, so for example, hydrogen has the electron configuration 1s1. All right, this 1s2, 2s2, 2p6 business, that's what I'm talking about here. So hopefully this rings a bell. This is what we're going to sort of review how to put together here. We're going to see it's going to be important for understanding these complexes, is being able to understand the electron configurations of these transition metals. Just a note here, so the superscript, this is what tells us the number of electrons. It tells us where the electron, in this case single electron, lives, which is this 1s orbital. All right, the S tells you the shape of that orbital. And the 1 out front tells you the relative size. All right, so what this electron configuration for hydrogen is telling us is it's got 1 electron in a small s orbital, which is for spherical shape. We can just kind of review real quick. We have these orbital shapes. And this is by no means how these were actually sort of established here, but we have kind of just a simple way to remember. An s orbital is that spherically shaped orbital. So your electrons are trapped in a little circle-shaped cage. Your p is a peanut-shaped orbital. That did not work. The d is a daisy-shaped orbital. It's like 2p orbitals combined. And there's also f orbitals, which we say are kind of flower-shaped, but really they just look kind of crazy. And I'm not even going to try to draw them. Doesn't really matter. All right, and I guess just to kind of review here also, this word orbital we're going to throw around a ton. Again, this electron configuration tells us where our electrons live. These orbitals are like electron cages. Within the atom, the electrons are trapped within a certain space, and it turns out that that space has these different shapes. So an electron that lives in a spherical shaped orbital, an s orbital, it's kind of trapped in this little spherical cage. It can jump around anywhere within there, but you won't find it outside of that cage. Likewise, if you have one of these more funky shaped orbitals, like a p orbital, that means that your electron is sitting here bouncing around between these two spaces, and again, you won't really find it outside of that peanut-shaped orbital, right? So these are these electron cages, these orbitals. Hybridization is when you start making molecules, so when you start making covalent bonds, and we won't be talking about those. We're just going to focus on the central metal ion and its electron configuration. We'll beat hybridization to death in organic chemistry, but for right now, we're just going to chill with atomic orbitals. All right. So where did this crap come from? Like, how do I know that hydrogen's got an electron in a spherical shaped cage? Who made up the peanut shaped ones? Like, what is all that business, right? So importantly, this all comes from like a giant math equation, all right, which we don't have to know any real math of, but just kind of because it's fun to look at here. Let's see if we can find it. Oh no, I don't know where it is. Anyways, it is what's called, so let's just say, where did this come from? All right. This is this fundamental theory in quantum mechanics called the Schrödinger equation. This dude, Schrödinger, I think everybody's heard of Albert Einstein. Schrödinger was very much so at that like Einstein level at the exact same time. They were contemporaries of one another. Einstein's got a lot of claim to fame. He did some great stuff. Another big name around that time, I just split open my nose somehow. It was Schrödinger. So he made this equation, and that's where this theory of where these shapes come from. All right, so when we're talking about our periodic table here, we need to cut this up into these different blocks. All right, so assigning electron configurations. Oops. All right, and so step one is what we're going to call cut up the periodic table. Into these blocks, these different orbital shaped blocks. Okay, so my periodic table here, everybody just take a second, get a rough sketch of like the outline of a periodic table. It does not have to be perfect at all. These are pretty big blocks we're gonna cut this into. All right, but one of the first things we're going to do is we're going to move helium over. It's kind of in the wrong spot. We group it with our noble gases because it behaves like a noble gas. It's got a complete octet, but its octet is a lot smaller than all of our noble gases. It really only has 2 electrons that it can fit. So we're going to put it back over here by hydrogen. Cool. All right, the first block on our periodic table is these first 2 columns. And this right here is our S block. All right, S, that spherically shaped orbital. Over here, this is our P block. Our transition metals, they live in the very middle here. This is our D block. Turns out that the fact that they have these D orbitals is really important for why they form these complexes to begin with. All right, and the ones that we will really just not talk about very much at all are the ones we kicked off the main part of the periodic table and gave this little block down here. We call the F block. All right, so we cut this periodic table into these different blocks. These are what's going to help us figure out the electron configuration for our particular element. All right, next we're going to number the columns in each block. This is going to correspond to the number of electrons. All right, so just for each block, I'm going to skip the F block just for saving time here, but I'm going to number my columns, 1, 2 for the S block. Starting over again, I'm going to count 1, 2, 3, 4, 5, 6 for the P block. And then starting with our D block, again, starting over at 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so just note that based on our numbering here, this is saying that you can fit at most 2 electrons in an s orbital, 6 electrons in a p orbital, and 10 electrons in a d orbital. If we did number the f orbital, you'd see that that would be a total of 14 electrons you can fit in there. All right, and so the last step is we're going to number the rows in each block. This is what's going to correspond to what we call the principal quantum number, or the one that tells us about the size of that orbital. All right, and this is the only one that kind of has a little bit of a trick to it. For each block, you're going to start at a different number. For S, we're just going to start at 1. All right, so what do I mean by that? If I look at my rows of my S block, I'm going to start numbering from top to bottom here, and I'm just going to start at the number 1. All right, so we got a total of 7 rows in that S block, starting at 1. All right, but when I go to my P block, that first row is not going to be row 1. I'm going to start numbering at 2. So the first row is not the 1P row, but 2P. Then 3, 4, 5, 6, and 7. All right, if I'm going to do my D block, so S was 1, P was 2, what do we think we're going to start at for D? 3. And F, we would start at 4. So not the worst trend in the world to keep track of, but we do have to remember, we start our numbering different. There's no such thing as a 1D or a 2D. It starts at 3D. All right, and then F, again, we start at 4. So that would be the 4F row and the 5F row. All right, so let's just kind of go over again, remind ourselves of what we said. Hydrogen was 1s1. If we look, that is because hydrogen is that first column Remember the number of electrons. And it's in that 1s row. So that's how I got my orbital. All right, so the location of the element on the periodic table helped me figure out what its electron configuration is. If we wanted to do helium, using that same logic, helium's right here. What would be the orbital? Also 1s. And how many electrons would be in there? 2. Cool. All right, so first 2 down. Not too bad. All right, now we're going to graduate to a larger element like lithium. Okay. According to lithium's position on the periodic table, lithium's just this third element. Now it's in the 2, the second row of the s block. All right, so 2s. And how many electrons are in that 2s orbital? Just 1, because it's in that first column. All right, but here's the deal. If I have a neutral lithium atom, how many electrons is it going to have total? It's got to have 3, because my atomic number is 3. So where are the other ones? All right, so when we build our electron configuration, the position of the element on the periodic table tells you the last orbital in its electron configuration. And then you got to include everything that came before it, all those smaller orbitals that came before it. So lithium also has a full 1s orbital, right? So I'm going to look, element 3. I'm going to look for where element 2 is. All right, that's this set right here. So here's my 3 electrons in a lithium atom. 2 of them are in a teeny tiny sphere, and 1 of them is trapped in a slightly larger sphere. All right, again, that principal quantum number tells us the relative size, and that s tells us that they're that spherical shape. Cool. All right, so I want you guys to take a second then and tell me what nitrogen's electron configuration is based on what we've been doing here. All right, so nitrogen, it's here in this 2p row. So my last orbital is that 2p. And how many electrons are in that 2p orbital? My column number, 3. But now we got to include everything that came before it. So what's everything that came before it? All right, so I got my 2p. That takes care of this here. What goes in front of that would be this row right here, which is what? 2s. So it's also got a full 2s2, 1s2. So everything that came before it. All right, so what you'll notice is the larger the element, the more and more orbitals it has, because the more and more electrons it has. All right, so then for the sake of fun here, let's do one of our transition metals, the focus of this chapter here. All right, actually we're going to do 2 of them here. Let's do iron and argon. Not a transition metal, but we're going to build to something here. All right, so for the sake of practice, everybody take a second and give me the electron configuration. Here's iron on our periodic table, and here's argon on our periodic table. All right, so you can kind of think about it either as starting here and then going backwards, or, starting at 1 and marching your way through the periodic table until you get all the way to iron. Regardless, we'd have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Because it's in that 6th column of that 3D row. Right? Remember, we started numbering that D block at 3. Okay, if we did argon, it would be 1s2, 2s2, 2p6, 3s2, 3p6. So again, the larger the element, the more and more electrons it has, so the more atomic orbitals it has. If I picked something all the way down here on the periodic table, it would be this huge, obnoxious task to give me that electron configuration, right? Because it's going to include all of those orbitals that came before it. Cool. So instead, we have a little bit of a shorthand that we can use. All right, what we call our noble gas abbreviation. All right, as we said, iron's electron configuration. Let me just copy that down again. All right, and then we had our noble gas argon. All right, and what we want to notice is that there is an exact match of argon's electron configuration found in iron's electron configuration. Right? They got the exact same orbitals up until this point here, this 3p6, and then it had a few extra ones on there, a few extra electrons. All right, so we can abbreviate iron's electron configuration by saying bracket AR. All right, and by putting AR in brackets at the beginning here, what we're saying is insert whatever argon's electron configuration is. So then if I wanted iron's electron configurations, that would be argon plus that extra bit at the end here, my 4s2 3d6. Right? So I would have to include that in my electron configuration for iron down here. Cool. So we can use this noble gas abbreviation, and that just saves us some writing. All right, by saying bracket argon, I'm saying insert argon's electron configuration, and then add 4s2 3d6 to get iron. Cool. So then, again, for the sake of practice here, let's do rhodium's electron configuration. Here's rhodium on our periodic table, element 45. All right, which noble gas am I going to use? Krypton. So I'm going to say, all right, whatever kryptons is. So that gets me up to here. I still got to include what comes after it, which is these two 5s electrons, and then our 7 4d electrons. So 5s2, 4d7. The p's are all accounted for in kryptons. If I were to say have chosen iodide, then you would have some extra p orbitals on the end here as well, p electrons rather. But since rhodium's in the middle here, it doesn't have any 5p, and all those 4, 3, and 2p electrons were accounted for in kryptons. Cool. All right, so we have these electron configurations. They tell us where electrons live in our atom. We can use these noble gas abbreviations. There are these two pain-in-the-butt exceptions to these filling rules, what we call the D4 and D8 exceptions. All right, by D4 and D8, I mean elements that live in the 4th column of the D block, and not D8, I'm sorry, D9. And the 9th column of our D block. So, sorry, D4 and D9 exceptions. All right, so why do these exceptions exist? It turns out that there's something special about half-filled or fully filled orbitals. These half-filled or fully filled orbitals are just extra stable. And our noble gases are very happy because they have just all of their orbitals completely filled up. All right, we can also note that this exception is only going to be true for D and S electrons. Turns out they're fairly close in energy compared to the other ones. All right, so let's take a look at one of these D4 elements. We're going to look at chromium. Everybody just take a second and give me the electron configuration for chromium that we would expect based on these filling rules that we've discussed. No, you could just do the abbreviation. We can pretty much default to the abbreviation from here on out just for making our lives easier. All right, so what we would expect for chromium is argon plus 4s2 and 3d4. All right, well, remember we said there was something special about being fully filled. So this s orbital right here is happy. It's fully filled. maximum number of electrons possible. So that's a good thing. But this 3d4 orbital here, this is only partially filled. There's nothing special about that, right? It is neither half nor fully filled. So, since these s and d electrons are so close in energy, what chromium's going to do is be like, all right, I got a plan. I'm going to instead move one of those electrons from that 4s orbital, so now there's only one electron in that 4s orbital, into that 3d orbital. So now I got 5 in that 3d. And so why would it want to do that? Well, because now the s orbital is half filled and the d orbital is half filled. And there's just something extra stabilizing about being half or fully filled. Right? So what we want to note here is the difference in the filling of these orbitals between what we would expect based on its location on the periodic table and the actual electron configuration. Our actual electron configuration is 4s1, 3d5. Okay, if we took an example from that D9 set of elements, we'll just do copper. We would expect copper to be argon 4s2, 3d9, where one's full, but the other's partial. All right, instead, what is copper going to do? It's going to move one of those electrons from that 4s orbital into that 3d orbital. I don't know why this won't. There we go. So now it's got one electron in its 4s and a full 10 electrons in its 3d. So now it went from being full and partial to half and full. Win-win. Okay, so again, we want to note the difference in the number of electrons in our 4s orbital from what we would expect to what it actually is. Where did that electron go? It was added to that 3d orbital. All right, in fact, that is the root of our exceptions here. We moved the electron from the s to the d orbital in order to get that more favorable electron configuration. Yeah, a little bit, maybe 6. Something like that. Yeah. Cool. All right. So one more thing with regard to these electron configurations we got to review. And really what we're going to be focused on is not so much transition metals, but these transition metal ions. All right. So what is the electron configuration of an ion? All right, so first of all, one that we did earlier was this iron atom, so a neutral iron atom. All right, well, what if I want to form the iron 3 ion? What is its electron configuration going to be? They're under here. Yeah. So first of all, that's a good guess. What are we going to have to do to this electron configuration? Importantly, right, this represents all the electrons that are in that iron atom. So if I want to form an iron ion, what am I going to have to do? Take electrons away or add electrons? I'm going to remove 3 electrons from this electron configuration here. Right? This represents all the electrons in an iron atom. Let's get rid of 3 of them. Then we'll have our iron ion. Okay, and so we have this kind of simple rule. We got to pull electrons away here. We're going to remove from that outermost s orbital first. Then from the d orbitals. All right, so I need to get rid of 3 electrons. I'm going to take my configuration here. I'm going to start scratching electrons. I'm again going to first remove those 2 4s electrons. All right, I still need 1 more to get rid of. So that I'm going to take from that 3d. So my electron configuration for the iron ion is argon plus 3d5. That's a good question. We're not going to have to worry about that since we're exclusively focused on our transition metals. The other thing is p-block elements. They tend not to lose electrons but gain electrons, right? Our non-metals like to form negatively charged ions. And so they just like to have their p orbitals fully filled up, and then they're super happy. Okay, so then for the sake of practice, I'm just going to, what was the other one we did? Rhodium, which was krypton, 5s2, 3d7, question mark? Yeah, no problem. Yeah, 3d7. Cool. So then everybody's going to take a second and tell me what the electron configuration would be for the rhodium-4 ion. Oh, I'm sorry, 5s2 4d7. Duh. Okay, so I'm going to take my electron configuration. I'm going to need to scratch 4 electrons here. So I'm going to take those 2 5s, and now I'm going to need 2 more from that 4d, leaving me with krypton plus 4d5.
The last 2 examples, they both ended up at a half-filled d orbital. Is that why transition metals take the oxidation states that they take?
That is not the only factor. Iron does like to form iron 3 ions. It also likes to form iron 2 ions. So it's a little bit more complicated, right? Because they can have multiple different oxidation numbers, charges. But yes, that is certainly a factor that you'll see, a trend that you'll see is that they like to form either half-filled or fully filled orbitals. Yeah, that same principle that we were talking about does apply. Cool. All right, so we got our electron configuration business out of the way here. Crash course in everything electron configurations from general chemistry. What we're going to see is that understanding these properties is going to depend on what the electron configuration is of these ions And so oftentimes when we start talking next class period about crystal field theory, we're going to start with these electron configurations of our transition metal ions and sort of analyze them from there. All right, the last thing that we're going to learn how to do today, and this goes back to the actual complexes themselves, is learn how to name these things. All right, so we're going to have this constants page here. We're going to learn how to use this. First, I'm just going to show you one of these with its name. You're going to trust me that I'm not lying to you. We'll pick it apart, and then we'll go from there. All right, so this was kind of the condensed structural formula of that ion that we sketched out, that complex rather that we sketched out at the beginning of class. Iron in the middle with its 4 water molecules, and that complex had that net charge of +3. All right, if we were going to name this thing, this would be tetra aqua iron 3. All right, what does that prefix tetra mean? 4. So that's how many of those ligands I have. In this case, I had 4 waters, so that's where the tetra comes from. And the aqua is the name of that water ligand. So all of our ligands, they have fancy names associated with them, and that's going to be that portion of our name. The iron is, of course, that transition metal. All right, and then the 3 here. Okay, we got to be careful. It's actually not the net charge of my complex, although it happens to match it for this here. This is the oxidation number. AKA just the charge, since it's simply a monatomic ion of that transition metal. All right, since my water has a no net charge associated with it, they match in this case. All right, we're going to do another example with a neutral ligand, but let me just show you these 2 charts here. So that first part of our name was the number of ligands. All right, that's what this chart here is for. Given the number of ligands, we have these prefixes that we use to refer to the number of ligands. All right, and then the second part of the name was the name of that ligand. If we look, H2O here, our ligand name is aqua. All right, so that's that second portion of our name. Again, we got a bunch of ligands listed here. Here are their chemical formulas. We can note some of them are charged, other ones are neutral. All right, and then the name of those ligands. What's up?
What's the one with no name?
Its name is just the same as its formula, EDTA. It doesn't have a special name. All these other ones have special names. Even insofar as like we call it a carbonate ion, but as a ligand, it's a carbonato, which is pretty cool. But yeah.
Will you want us to memorize the ligand names?
No, so this is a chart that you'll be given on a constants page. So the name of the game here is not memorizing, but knowing how to use the tools, right? And so that's what we're going to go is, how do I piece together these 2 charts to get my name? So let's just do an example here. We're going to do cobalt NH3 6 plus 2. All right, and just given our example, starting with first the number of ligands, Then the name of the ligand, the metal name, and in this case, I'll tell you its oxidation number does indeed match that net charge because, again, we're talking about a neutral ligand. NH3 is neutral. See if you can't put together the name of this complex here.
The name is always one word, no spaces.
Yeah, it's just rammed together really elegantly. All right, CO, if for, in case you don't have our periodic table memorized, CO is cobalt.
Since there's two A's, is it just going to be just
No, you ram them all together. Just
so yeah.
AA.
Oh, really?
Yep.
Oh.
Hexaamine.
What would the cobalt be called here? Like, what's the, in parts, what would that be called?
The cobalt is the central metal ion in our complex. Yep. Okay, so the first part of my name is going to include the number of ligands. So 6, we're going to use this prefix hexa. And the second part of my name is the ligand name itself. And in this case, NH3, when it's all by itself, we call it ammonia. But in our complex, we call it amine ligand. All right, so this would be hexaamine cobalt 2. Hexaamine cobalt 2. Beautiful name, right? If you go and get some goldfish and you're looking for name ideas, you can look to these transition metal complexes. Beautiful, all right? Now, in this case, again, we had this neutral ligand. So let's pick one of these other ligands that are not neutral here. So we're going to do an example with a chloroligand. All right, we'll still get our ligand prefix chart here. Let's do Cr chromium Cl4 with a +1 charge. All right, our first step here is actually we got to figure out what the oxidation number, aka the charge on that chromium is. All right, so how are we going to figure this out? Well, remember the sum of our oxidation numbers, they have to equal the net charge of that complex. So my chromium plus those fluorochloroligands, they all have to equal that net charge of +1. All right, and I got too many missing variables here, but which one of these do I know? I know the charge of my ligands, right? Notice that all ligand charges are listed on this chart here. So my chromium I don't know, but I know that each of those chloroligands have a charge of -1, and that all has to sum up to that net charge in my complex of +1.
Yeah, so would it just be the final like charge minus whatever the total charges from the ligand and like multiplied by the amount of like it's there or whatever?
Yeah. Yeah. I mean, basically you're going to subtract this from your net charge.
Right.
Yeah. All right, so that means my chromium must have a charge or oxidation number, if we want to be fancy, of +5. Right, and importantly, that's what gets built into the back half of the name, not the net charge, but the oxidation number. All right, so I'll zoom back out here. Everybody take a second and name this one for me. All right, my number of ligands, I got 4 of them. My chloride ion we call a chloroligand. So this would be tetra, chloro, cobalt, 5. Chromium. Ayo. I wish I could say that. My brain's just still on spring break a little bit. All right, chromium 5. All right, cool. So we kind of see how we need to piece these things together. Again, not about memorizing anything, but being able to use this chart that you'll have on your constants page. All right, up until now, all of these examples that we did were of positively charged complexes. And that's not always going to be the case. So we have a little extra step that we have to do for anion complexes. All right, so let's just put an example here. Cu F5 with a -3 charge here. This is our anion complex. Anion because our complex has a negative charge. All right, so the first few steps are actually the exact same. I want everybody to first tell me what the oxidation number is of this copper in this complex. Same process we did before. All right, so my copper plus those 5 fluorines has to equal that net charge of -3. I don't know what copper is, but according to my ligand chart, each of those fluoroligands has a charge of -1. So what -5 is going to leave me with -3? That copper must be 2. All right, so we're going to now build our name using these first 2 tables the same way. We have 5 of those fluoroligands. So pentafluoro. All right, but now we see this other chart down here. Okay. When we have a positively charged complex, we refer to the metals just by their normal metal names. But if they're in a negatively charged complex, we have a special name for those metals. Usually you just tack 8 onto the end, or sort of some form of that. Some of them are a little bit more fancy. So for copper, when it's in an anion complex, you use the word cuprate. So this would be pentafluorocuprate 2. Again, rolls off the tongue. No, it does not. It does not solve some sort of ambiguity. It is something that you see. I don't really know if it had historical reasons, but you do see this a lot. It's with our polyatomic ions too, right? A permanganate ion, because it's got a negative charge, sulfate, phosphate. You see this kind of convention carry over quite a bit. But yeah, anytime it's got a negative charge, we don't just refer to it by its metal name, but by its anion name here. The anion names? Well, some of these you can also see kind of their origins, right? Gold is aurate. It's also Au on the periodic table. That's kind of the Latin roots of that term. So I'm imagining this is pretty old school chemistry here where this all comes from. Yeah, ferrate, Fe on the periodic table. Exactly.
Is it maybe just to like verbally identify like, oh, they're coming from an anion complex versus a cation complex? Because like, I don't know.
Yeah, I mean, but like you said, that you would be able to figure that out if you knew what the ligand was and you knew what the oxidation number was. So it's not like it's an essential piece of information. It's a convention, though. I don't make the rules, especially not IUPAC rules, especially not nomenclature rules. All right, but yes, bottom line here is we have one column for our negatively charged complexes and another column for our positively charged complexes. Cool. All right, so then one more curveball that I'm going to throw at you here. I've been hiding some information on this constants page. All right, it turns out that there's a little bit more to this here. Get rid of these examples. We got this extra column here and this extra column here. So what the heck is this for? All right. Certain ligands are what we call polydentate ligands. All right, these polydentate ligands, these are ligands that will form more than one coordinate covalent bond. All right, so what do I mean by that? One of these examples from our list here is what was called ethylene diamine. We just abbreviate it EN in our name. All right, if we looked at the structure of ethylene diamine, what we would find is there are these two carbon atoms. Each one has two hydrogens on it, but they're also both bound to a nitrogen, specifically an NH2, what we'll call in organic chemistry an amine group. All right, well, remember, our ligands are electron-rich. Nitrogen we'll see in a few of our ligands because nitrogen likes to have 3 bonds and 1 lone pair. That's its most stable state. So I got a lone pair on 2 ends of this molecule, right? One in the front, one in the back. And if we put this next to one of our transition metal ions, what we'll see is that it forms a coordinate covalent bond with 1 lone pair. But then it kind of wraps itself around that ion and forms a second coordinate covalent bond with that other lone pair. All right, so this single ligand here is able to form 2 coordinate covalent bonds with that central metal ion. What's up?
So what happens if you have like the
Yeah, so typically you can have mixed complexes. They certainly exist. Typically the affinity of one versus the other will be greater, and so you'll have like this equilibrium that usually favors one form over the other. Nitrogen is a little bit better at being that Lewis base than water is, for example, so it kind of outcompetes it. So it's not like you don't have complexes that have mixed ligands, but you don't have to worry too much about that.
Considering the name, we would just go with the stronger one.
Okay, I see where you're going. We'll do one example of that towards the end here. But for right now, we don't have to worry about predicting what it would be like. If I put iron 3 in a mixture of water in this thing, what's my complex going to be? That's kind of a big, ugly math equilibrium problem that we don't have to worry about. In terms of naming stuff, we can do that. But importantly here, let's finish our bases with our polydentate ligands. These ligands that form more than one here, okay? More than one coordinate covalent bond. Importantly, we call these, in this case, these nitrogens would be donor atoms, the things donating those lone pairs. Okay, so that means that a polydentate ligand necessarily has more than one donor atom. Right, the ability to form more than one of those coordinate covalent bonds. All right. So if we look, that's what this extra piece of information is on our ligand chart here. It tells us for each ligand how many donor atoms they have. If you go through the examples that we've done previously, I kind of specifically chose ligands that only had one donor atom. All right. If we pick one of these ligands that has more than one donor atom, then all of a sudden we have to use our polydentate ligand prefixes rather than our monodentate ligand prefixes. Again, I don't make the rules. There's no logic as to why they had to have a different set, but they do. All right, so if we have one of those ligands with more than one donor atom, we're just going to use a different prefix for those ligands. All right, so let's do one last example here. All right, we're going to do zinc. With 3 carbonato groups and a -4 charge. Oh, whoops. Need that bottom of that chart. All right, so we have this oxidation number of 2. When we're going to do our number of ligands, we have 3 of them. But noting that this carbonato ligand here has 2 donor atoms, I'm going to have to use my polydentate ligand prefix of tris instead of tri. All right, so doing my name here, make a little bit more room for myself. All right, tris, carbonato. Am I going to use the metal name or the anion name? Zinc or zincate? Zincate, because my complex had that negative charge. So tris, carbonato, zincate, and then that oxidation number of 2. All right, so first thing to note, we have to use that polydentate ligand prefix. All right, there's one more pain in the butt aspect of these polydentate ligands, which is that when you build the name with them, the name of the ligand goes in parentheses. All right, so we have to use parentheses for that polydentate ligand. Cool. All right, so now we can name these things, so we're going to be able to talk about these complexes. All right, we have this constants page here with these 3 charts, tables rather. Using these tables, we can construct the name of our transition metal complexes. Cool. All right, we ran 5 minutes over here, so we'll start lab 5 minutes late here. We'll pick things up at 2:35.